without truncations?
In
I have seen the graphs and other things. That's okay. Apart from that, in the as an overall structure, I am asking.
Until now, not compared. Just studied based on the truncated distribution.
Okay. Because it has two things. I don't know whether one may be a plus, another one may be a minus, in the sense that if it is a correct truncation, I think it's going to be a plus, and if it is somewhat not up to the correct one, it may be something like missing some information. So loss of information, which may cause some drawback to the process or whatever may be the thing, okay, in which it is going to be used. So
thank you. I will check that. I'll check this.
Yeah. So you may have an eye on it, and that's a good presentation. Once again, we'll congratulate the presenter, and we'll move to the next candidate.
Thank you, sir. Thank you.
Yeah. And the next candidate is. Yes, Sarida, the topic is double prior selection in Bayesian estimation for parameter of variable exponential distribution. Madam, please proceed.
Okay. Good afternoon, one and all present here. I am going to present the paper double prior selection in Bayesian estimation for parameter of variable exponential distribution. Next slide, sir. Our background, aim, and objective of this paper, the variable exponential distribution is a 3-parameter distribution, is most widely used for analyzing lifetime data. The Bayesian approach is a non-classical estimation technique in statistical inference, and it is useful in real-world situation. The purpose of this study is to determine the estimation of parameter of the variable exponential distribution. Main objective of this paper to compare between the MLE and Bayesian procedure for estimating the shape parameter of the variable exponential distribution. Here, stimulated data is used for comparison. Model description: x1, x2 up to xn be the set of n random sample from variable exponential distribution with parameter alpha, beta, lambda. Here, alpha, beta are the shape parameter, lambda is the scale parameter. The probability density function and cumulative density function for variable exponential distribution is given in equation number 1 and 2. Next slide, sir. Next, we see the various stages of study on the variable exponential distribution using Bayesian quadratic loss function. First, we have to estimate the shape parameter of the variable exponential distribution by using the method of maximum likelihood estimation. It is given in equation number 3. The likelihood function for the parameter alpha is given in equation number 4. The log likelihood function is given in equation number 5. Differentiating equation number 5. So previous slide. Differentiating equation number 5 partially with respect to alpha, equating to 0, we get equation number 6. So alpha cap is the estimator for the shape parameter of the variable exponential distribution.
Other presenters, please mute themselves. Other than the presenter, okay. I think others, please.
Next,
mute.
Forming the prior distribution. Here we using double prior, gamma, and uniform distribution. The first prior distribution for alpha is a gamma distribution with hyperparameter A and B. It is given in equation number 7. Second prior is assumed to be a uniform distribution. It is given in equation number 8. Double prior is defined as the product of density function. It is independently distributed. That is pi of alpha proportionate to pi 1 of alpha into pi 2 of alpha. Combining these two distribution, we get the equation number 10. Next slide, sir. Next, we are determining the posterior distribution. The posterior distribution is expressed in equation number 11. The posterior distribution of the variable exponential distributions follows gamma distribution with parameter alpha, which is equal to a plus n, beta equal to summation e power lambda xi minus 1 all power beta plus b all power a plus n. Next slide, sir. Next, we are estimating the parameter of Bayesian estimator through self and quadratic loss function method. The quadratic loss function is defined as L of alpha cap comma alpha. Here, alpha cap is the estimator of the parameter under quadratic loss function, which is equal to alpha cap minus alpha divided by alpha the whole square. The derivation of Bayesian estimator using quadratic loss function under double pi r, it is given in equation number 12. Next, Bayesian estimator of self is defined as L of alpha cap minus comma alpha, which is equal to alpha cap minus alpha the whole square. It is given in equation number 13. Next slide, sir. Next, we see the result and discussion based on simulated data to compare the MLE and Bayes estimator under self and quadratic loss function. Simulation study was carried out. Your samples are generated from variable exponential distribution with n is 1000 for different sample size 10, 20, 40, 100. It represents the small, moderate, and large sample. It allowing the shape parameter alpha and fixing the hyperparameter lambda, beta, A, and B, and estimated values are shown in the table. The calculation are performed by using the package R. For the shape parameter alpha, it is found from the equation 14, 15, 16, and mean square error is given in equation number 17. Next slide, sir. These are the results for parameter estimation by using MLE and Bayes with respect to mean square error for different values of alpha. Your hyperparameters are fixed. So when sample size increases from the table, what we have find when sample size increases, estimated value also increases, mean square error will be decreases. When we compare with MLE and Bayes estimator, so quadratic loss function is the best estimator. So next slide, sir. Next slide. Next slide. Next conclusion. In this study, for estimating the shape parameter of a variable exponential distribution was developed based on double prior selection. This approach was adopted from Bayes' point of view. Double prior probability distribution for the parameter alpha, we assume gamma uniform distribution. Comparison based only on MLE and Bayes estimator with respect to mean square error. From the table, we propose Bayes estimator performed better than MLE for estimation when sample size increases with different values shape parameter, MSE decreases. On comparing with all the estimators, quadratic loss function is the best estimator. Next slide, sir. Some of the references. Thank you, sir.
Yeah, very good and time-bound presentation. Any questions from the audience?
Sir, I ask one.
Vishwanath, go ahead. Suresh, go ahead. Go ahead, Suresh.
Suresh, you unmute your.
Madam, I have one doubt, ma'am. Ma'am, in your simulation studies, you have to fix the parameter value, hyperparameter value A, comma B, and beta value is equal to 1. Why is there any criteria you have followed to fix the parameter value? Or
no, sir. Just we assuming the hyperparameter fixing the value.
Why we can't assume 2 or 3 like that?
We can assume, sir.
Any criteria is follows? You have followed?
No, sir. No criteria. You can assume 3, 4 also, sir.
What is the range for the parameter A, comma B? What is the and beta?
Beta, we assume one.
No, what is the range for the parameter?
Range for the parameter value.
Yes, beta.
Beta is greater than 0.
Okay. Okay, madam. Thank you.
Okay, thank you.
Yes, Professor Bala, you can proceed.
Yeah, I have one just a clarification. In the first slide, you mentioned that this will be used in a real life problem, but it would be nice if you throw some light on using this distribution with a real life problem. And the second question is, you're comparing the maximum likelihood estimation with the Bayesian modeling. To my understanding, and everybody's known about the Bayesian, you need to have a prior and posterior information where the posterior informations are unknown. But whereas in the maximum likelihood modeling, everything is known. Then when you're comparing, how do you compare these two estimates? Because it looks like you're comparing apples with oranges, not apple to apple. It seems to me that the comparison is not quite correct. Maybe I'm wrong, but some of them, the theoretical statisticians in this group, maybe throw some light on that.
Okay, sir.
Any justification, madam? Okay, I too agree with Professor Bala in the sense that we cannot compare MLE, which has no information about prayer structure, because Bayesian has a prayer information on prayer structure, which is more advantageous to the structure. So, normally comparing MLE with the Bayes, in my opinion, also I agree with Professor Bala. So it's not a valid comparison. And any other question from the audience? Okay, if no other question, I think we can appreciate the presenter, and you can make note of things provided by the learned audience, and you can improve accordingly. It's
Okay, sir.
a good presentation. We congratulate the presenter. Thank you, madam.
Thank you, sir.
Next presenter is Shanmuga Sundaram. The title is Bayesian Survival Analysis of Exponential Distribution based on type 2 sensory with double prior selection.
Yes. Good afternoon to everyone. My presentation covers Bayesian survival analysis of exponential distribution based on type 2 sensoring, double prior selection. The next page. Background name. There are a lot of lifetime distributions which is often used in survival model. I use 2-parameter exponential distribution, which is one of the lifetime distribution. The purpose of this study is to determine the estimation of the parameters of the 2-parameter exponential distribution and apply them to simulated and real data. The time distribution of survival is usually described in 3 functions, namely survival, probability density, and hazard function. The main objective of the survival study is to estimate the parameters using Bayesian squared error loss function method with double prior selection for scale parameter and the single prior for second parameter using type 2 sensor data and maximum likelihood estimation to estimate both parameters and compare it with mean survival time and its MSC. Model description. As per definition, survival function defined as an probability stating that an individual can survive until time t. If x be the survival time of the continuous random variable that follows the 2-parameter exponential distribution with parameter theta and mu, then the PDF or CDF are given in equation 1 and 2. The survival function and hazard functions are determined and given in equation 3, which is e power minus x minus mu by theta, where x is greater than mu and theta is greater than 0, and the constant hazard rate 1 by theta. And next, estimating the Bayesian estimator using squared error loss function. First, we have to set the likelihood function for the type 2 sensor data, which is given in equation 5, where n is the total number of samples and the test is terminated after the R event. The x1, x2 of x are the R observed ordered failure times during the test. The likelihood function for the type 2 sensor data for the given 2-parameter exponential distribution is given in equation 6, that is 1 by theta power r e power minus x by x minus mu by n, mu n divided by theta, where y is sum of all observed order failure times plus n minus r into orth order failure time. And second stage, forming the prior. Here for the scale parameter theta, using double prior, 2 information for a single parameter. The inverse gamma distribution is the first prior with hyperparameter alpha and beta, which is given in equation 7, and the second prior is non-informative prior, which is a free prior, which is determined as 1 by theta square, given in equation 8. Combining both priors, double prior distribution is given in equation 9. And for parameter mu, uniform prior is considered with density 1 by beta, where mu lies between 0 and b, 1 by b, sorry. Next, determining the posterior distribution, the joint posterior density of theta and mu is given in equation 10, and the c is constant given below. The marginal posterior density. The marginal posterior density for theta and mu are determined and given in equation 11 and 12. Next. Estimating the parameters of Bayesian using loss function. Here I use squared error loss function defined as theta cap minus theta the whole square. Using self, the estimated parameters theta and mu determined given in equation 13 and 14 is theta cap and mu cap. And second estimation method, maximum likelihood estimation. The MLE estimator of type 2 sensor data for the two parameter exponential distribution is determined using the log likelihood function of the type 2 sensor data, which is given in equation 5. The determined estimates are shown in equation 15 and 16. CMLE denotes sensor MLE. Application to real life data. Data given below represents the time between successive events. The times are exponentially distributed with n equal to 25. For this data, the Bayesian estimators theta cap, mu cap, and the survival rate, hazard rate are determined. For the prefixed R 18, the values are estimated and shown. The survival rates are for the 18 values are tabulated with the constant hazard rate 0.37506 Go for survival and hazard rate. First one is for survival and second hazard rate, which is constant. Next. Simulation study. A type 2 sensor 2 parameter exponential data was simulated using our program to compare the estimated survival rate, different estimation methods. The data was simulated for the sample size n equal to 15, 40, 50, and the parameter value theta equal to 1.5, 2.5, and mu equal to 1. And different R are chosen according to their sample sizes, and the mean survival rate for every combinations and their respective MSCs are noted and tabulated for comparison. So the tables, the table 1.1 contains mean survival rate and MSC for both estimators for n equal to 15 and theta equal to 1.5, mu equal to 1, along with R, different R according to their sample size and censorship percentage. From the table 1.1, previous slide please, sir, few seconds. From this table, the survival rate decreases as R increases, and the MSC also decreases. Comparing with the Bayesian MLE, Bayesian MSC has less error. The Bayesian serves better in survival rate. Same results for all the other comparisons, combinations. Conclusion: estimation of two parameter exponential distribution parameters for type 2 sensor data by Bayesian self and MLE method is obtained as theta cap, mu cap, and theta cap CMLE and mu cap CMLE, and given in equation 13, 14, 15, 16. Survival rate and hazard rate for two parameter exponential distribution are also obtained. For real-time data, the parameters survival rate and hazard rate are determined and stated above. From the graph, the survival rate as able to know that as time increases, the survival rate decreases and hazard rate is constant. For simulation study, comparison of two estimates, mean survival rate with MSC found that Bayesian estimate has less error than the MLE estimate. It shows better. Next. The next slide is some major references. Thank you.
Yeah, again, a good presentation. Any questions from the audience?
Vishwanathan, I would like to comment on that.
Yeah, please proceed.
Shanmugam, it's nice
Yes.
presentation, and it looks like you have an abundance of theoretical background. I would like, I'm so happy to see you as a presenter from Presidency College. I'm also
Thank
one
you.
of the student graduated 35 years ago from the Presidency College in the same building where you are standing right now.
Yes. Thank you.
So I hope, it's fascinating to see that the students with so much enthusiasm and interest in the statistical literature. But I would like to suggest only one thing. You did a simulation studies using this method, but it would be nice to use a real life data, especially the survival modeling used a lot of sense in the cancer research. Take the cancer research data, you can see that how the survival goes into it. So then you will able to understand this theory much more than now.
Yes.
But happy to see you from the place where I stand 35 years ago. Nice.
Thank you, sir. Yes, sir. Actually the data, we have minimal time. That's only I used the data which is worked in the previous paper.
Good.
Thank
Right.
you.
Thanks.
Yeah. Any other question? Okay, if there is no other question, I think we can congratulate the presenter and we'll move to the next candidate.
Thank you.
Thank you, Sundaram.
Thank you.
So the next candidate is Mrs. V. Sasikala.
Good afternoon, sir.
Yeah, please proceed, madam.
My title of this paper is Selection of Repetitive Group Sampling Attribute Plan for given AQL and LQL involving minimum risk using zero inflated Poisson distribution. So next slide.
Yeah.
Abstract of this paper is acceptance sampling plan is product control technique used in industry to inspect the
Can the
quality.
organizers please unmute other people other than the presenter? Can the organizers please? Yeah. Okay, madam.
Yeah. The product of processing at various stages of manufacturing and the finishing product against a specified quality standard. Various methods are used for monitoring and maintaining the quality of the products and services. With the help of the sampling method, the quality of the products and services are decided to accept or reject. In this situation, the interest is to keep away from the wrong selection, that is, accept the product of bad quality and reject the product of good quality. According, the usual objective in these cases is used to overall risk for a wrong decision as optimization criteria. In the situation, this is called as a minimum risk sampling plan. Next slide, sir. So the main objective of the paper I have been taken, the zero inflated Poisson distribution has been used to select the parameter of a repetitive group sampling attribute plan involving a minimum sum of producer and consumer risk for specified acceptance quality level and limiting quality level. These are the notations, observation, abbreviation I have been used in this paper. Next slide, sir. The statistical performance of a sample test plan is shown by its operating characteristics curve, OC curve. In the non-basic interpretation of acceptance sampling plan, 2 points are generally indicated on the OC curve, namely P1 on comma 1 minus alpha and P2 comma beta. Due to the discreteness of the parameter of the sampling plan, the condition of fixed risk are often changed to P of P1 greater than or equal to 1 minus alpha and P of P2 less than or equal to beta, where P of P is the probability of acceptance for a given lot of process control P. The parameters of the sampling plan N and the acceptance number AC are set in such a way that the 2 points requirement is met with the minimum sample size. There are several purposes that must be met in designing the sample plan. According to Hamaker, the most important are to strike the right balance between consumer demand, the skill of the manufacturer and the skill of the inspector to separate defective plots or non-defective, and simplicity of producers and administration, a reduction in the number of observation, reduce the risk of wrong decision by increasing the lot size, use the sample data you have collected as a valuable source of information, put pressure on that manufacturer or supplier if the quality of the batch received is not reliable or does not meet standard. Reduce sampling if the quality is reliable and satisfactory. The main the distribution I have been taken zero inflated Poisson distribution. It has applied in a various field of study along the zero defects or in production process. It can be treated with a zero inflated Poisson distribution model. Under this situation, the study of the zero inflated Poisson can be found in Lambert. He derived that zero inflated regression inflates the number of zeros by mixing point mass at zero with the Poisson distribution. Mockning reduces a various application with the occurrence of a zero inflation. Sim and Lim have described that importance of zero inflated Poisson model in their research. To contribute, they have contributed the construction attribute control charts for monitoring the process under that zero inflated Poisson distribution. Next slide, sir. Here an attempt is made to study the repetitive group sampling plan for given acceptance quality level and limiting quality level involving minimum sum of risk using a zero inflated Poisson distribution. The zero inflated model provides a frequent zero observation when the production monitor is inspected. As a generic accounts, some of them may be zero. In the zero inflated model, the response variable is modeled as a Bernoulli mixture. The advantage of the zero inflated model is that can have a parameter called the zero inflation parameter that is a complement to the number of parameters in the underlying distribution. Good quality with a small fraction of defective is generally accepted and is called as a AQL. Quality that consumer is willing to tolerate only a small part of a accepted lot is called as a RQL. It is also called the lot tolerance proportion defective, and it is called as a UQL. According to the inspection plan, the plot is offered to the consumer with the label AOQ, and it is the maximum limit called AOQL that products. A random variable of X is said to have a zero inflated Poisson distribution. The probability mass function is defined as when the number of defective is 0, pi e plus of 1 minus lambda, sorry, 1 minus pi e power minus np is the probability function. If there will be a defective, the probability function will be 1 minus pi into e power minus np power d divided by d factorial. Here that np and pi are the parameters of the zero inflated Poisson distribution. Next slide, sir. So here I have been used that repetitive sampling plan. It is majorly provided by the Sherman. Sherman has provided the table for selecting the RGS plan using the slope of the OC curve. Following that, K. Subramanian developed the table of the RGS plan with the minimum risk sum. And K. Subramanian and Haridas constructed a table of selecting a single sampling attribute plan for given AOQ, AQL and LQL with a minimum sum of risk using weighted Poisson distribution. With the continuation of that, I have been taken that zero inflated Poisson distribution. The testing procedure of repetitive group sampling is we have to take a sample, random sample of size n. Then after that, we have to count the number of non-conformity D. If D is less than or equal to AC1, we have to accept the lot. If D is greater than AC2, reject the lot. If D is greater than or equal to AC1, less than or equal to AC2, we have to repeat the first and second step. Next slide, sir. Next slide, sir. So here I have been constructed in a table. The table is named table 1, is used to select the RGS plan for using AQL and LQL that involves their minimum sum of risk. The table 1 gives that acceptance number AC1 and AC2 and that associated producer risk and consumer risk alpha and beta in the body of the table against the producer of that sample size N and AQL. With a specified value of P2, P1, alpha and beta, that an RGS attribute map can be found from the table 1 as follows. Next slide, sir. The operating procedure of the RGS determine the operating ratio P2 by P1 that should be tabulated in that with the calculated value of P2 by P1 enter in table 1 in the row headed P2 by P1 in that equal to or less than or equal to the calculated ratio. To determine the parameter AC1 and AC2 proceeding from left to right in that line identified in step 2 so that the tabulated risk for that manufacturer and consumer are equal to or slightly smaller than the desired risk. The sample size n is obtained as n equal to np1 by AP1, where the value of NP1 are given in the header of the column that corresponding to the acceptance number in step 2. Table 1 can also be used to select the RGS plan when the sample size is fixed for a practical administration reason. For example, if we fix that sample size n equal to 30, AQL P1 equal to 0.2 2%, LQL is 3%, or 1 get NP1 equal to 300 into that are N into P1 equal to 3 and P2 by P1 equal to 2.25. Corresponding to that value of NP1 and P2 by P1, one obtained that the following involving minimum sum of the risk in the table 1 is presented in the last slide. Next, sir.
Madam, you have to make it fast. We are running over.
Sure, sir. Sure, sir. This is the function I have been used, that Sherman has derived that function to construct the OC curve. This is the function I have been used to for a zero inflated Poisson distribution. Next slide, sir. The advantage of minimum risk plan, tabular value relate to operating ratio that are frequently encountered in practice. The OC curve for the minimum risk plan have a better solder, that is the plan better differentiate between a lot of non-defective and defective qualities. If the producer and consumer belong to the same company of interest, the sum of the risk can be minimized instead of being fixed at a certain level. The conclusion of this paper we have been used optimization criteria to reduce the overall risk for a wrong decision. The plan tabulated here refer the operating ratio that are frequently encountered in practice. The sum of risk can be minimized rather than fixed at a certain level when the producer and consumer belong to the same company. The table 1 presented in the work was developed using the zero inflated Poisson distribution to select the repetitive group sampling pen. Based on the analysis performed, we can conclude that zero inflated Poisson distribution is reduce the sum of risk. Then OC curve for that, the zero inflated Poisson distribution also presented in the slide. It is for based on optimizing criteria. And these are the papers I have been referred. And this is the table for a repetitive group sampling for zero inflated Poisson distribution. Next slide, sir. And OC curve for that.
Yeah, it's again a good presentation. Any questions from the audience? Okay, if there is no question from the audience, then I will ask my own. Madam, if you take the normal Poisson distribution instead of zero inflated, right? What changes do you expect?
Zero inflated, actually it is the continuation of that weighted Poisson I have been taken, sir. Actually, it is coming from the zero inflated Poisson distribution is derived from the under this conditions of that condition of the binomial distribution. So that there will be two criteria. If the defective is there, that the probability function is different, and if there is a defective is greater than 1, that probability function will be slightly differ.
Yeah, that is accepted. But my question is, instead of using zero inflated Poisson, if you use ordinary Poisson, what changes you expect in your performance parameters?
Yes, we have reduced the sum of risk because that comparison I'm presenting in a journal that I have been studied that that comparison of the Poisson and weighted Poisson and zero inflated, that a zero inflated is the risk level is minimized than the Poisson distribution.
Okay, madam. Any other question? Okay, in that case, we can congratulate the presenter. And I think we can move to the next slide. Thank you, madam.
Thank you, sir.
So the next presenter is Mrs. G. Jayakudi. Our title is Statistical Inference on Competing Risk.
The slide is not belongs.
I think the slide, the PPT is different from the one the candidate is expecting.
Yes.
Sir, Karunya dana sir next.
Pardon?
Karunya.
Which?
Karunya. The Sasigala kapra Karunya dana sir.
Oh, okay. Right.
Sure.
Yeah, Karunya, please proceed.
Good evening, everyone. I'm myself Karunya from Department of Statistics, PSTCAS, under the guidance of Sangeeta. And today my topic is a design for double sampling plan of type 0,1 under a fuzzy environment. My abstract is acceptance sampling is the important aspect in decision making for a quality assurance, and it is useful in destructive testing of sample and reducing 100% inspections. The parameter of the sampling plan holds uncertainty. It can be expressed as crisp values, but in some cases it cannot be expressed as crisp values. In those cases, it is expressed as linguistic variables with the use of fuzzy set theory. In this paper, a design for double sampling plan of type 0,1 under fuzzy set theory is discussed. So next slide. Introduction. Acceptance sampling. Acceptance sampling is the important aspect in decision making. Decision making of products. Decision making of acceptance or rejection of manufactured products based on the inspection of samples. The major areas of acceptance sampling are lot by lot sample by method of attributes, lot by lot sampling by the method of variables, continuous sampling, special purpose plans. The introduction for fuzzy set theory is, fuzzy set theory is a mathematical model of uncertainty values generated by the experiments, and it is powerful tool to analyze the parameters that cannot be estimated accurately. To determine the uncertainty existing in quality characteristics in sampling plan by defining the imprecious parameter as a fuzzy number. Fuzzy set theory is useful to achieve higher certainty. This work mainly relates to the study on double sampling plan of type 0,1 using fuzzy environment. Double sampling plan is a plan in which decision to accept or reject a lot is based on inspection values of two samples. The parameters of double sampling plan are N1, N2, A1, A2, R1, R2. Sample of size of first sample, size of second sample, acceptance number for first sample, acceptance number for combined samples, rejection number for first sample, rejection number for combined samples respectively. The operating procedure for double sampling plan is given. Next slide. Operating procedure for the double sampling plan of type 0,1. From a lot, select a sample of size N1 and observe D1. If D1 equal to 0, accept the lot. D1 greater than 1, reject the lot. If D1 equal to 1, select the second sample of size N2 and observe D2. If D1 equal to 0, accept the lot, otherwise reject the lot. The probability acceptance of double sampling plan of type 0,1 is given, and the fuzzy probability of fuzzy double sampling plan of type 0,1 using a fuzzy Poisson distribution is given. Here N1, N2 and P are considered as fuzzy parameters and also considered as triangular fuzzy number. Using this fuzzy probability acceptance, fuzzy OC curve is derived. The fuzzy probability of acceptance of a lot in terms of fuzzy parameter is a band with upper and lower bounds. These bandwidths depend on the degree of uncertainty. The OC band under complete fuzziness indicate that when the lot quality is in a good state and the OC band is wider, and in a considerable state, the band with an arrow. The numerical example for this double sampling plan of type 0,1 is given. Suppose that the double sampling plan of type 0,1 with a fraction defective is approximately 0.01 and a fuzzy and the first sample size approximately 10 and a second sample size approximately 20, then the fuzzy probability of acceptance using fuzzy Poisson distribution is derived and the OC curves are given. Conclusion: the double sampling plan of type 0,1 is designed with fuzzy parameters. Here, Under the fuzzy environment, the sample size, acceptance number, and the fraction of non-conforming units are defined flexibly, and the obtained result shows that the whole possibilities of OC with the effects of fuzzy parameter, it helps to select the samples within the fuzzy OC bandwidth and helps in reducing the sample cost. These are my references. Thank you.
Yeah, a very crisp presentation rather than a fuzzy presentation.
Thank you.
Any question from the audience?
Yeah, Vishwanathan, one.
Yeah, plus. Yeah, please proceed.
A nice presentation, and she's able to complete it within the time frame. That's nice. One thing I noticed in the last figure example graph, the probability ranging from 0 to 1. Of course, the curve is within that 0 to 1, but I see the value is 1.2. So you need to be very careful about it. And that is only one observation. And my question next is, you talked about the fuzzy, meaning that doesn't have any control, right? There is a controlled environment and there is an uncontrolled environment. So the uncontrolled environment is a fuzzy. Is that correct?
Yes, sir.
You mentioned that in the topic fuzzy environment. What does it mean?
So we cannot predict exactly.
So does it mean that you don't have any control or the bandwidth to do your problem?
We can find a range.
You can find. That's one thing, Amma. You need to be very careful when you're defining what fuzzy environment is. Doesn't have any control. You can take any values without any boundaries. It's not a controlled set of values. So it would be nice to the audience when you start explaining what is fuzzy environment, how the fuzzy environment will be useful in a given situation. So that, of course, your presentation is nice. If you add one more slide to it, what is fuzzy environment, how it is useful, that would enlighten your talk. Thank you.
Thank you.
Thank you, Professor, for your useful comment. Any other question? If there is no other question, I have my own question. Madam, you have mentioned about probability of acceptance in one of your slides, probably in the 5th or 6th slide. Can you go to that? No, next. Yeah. See here, can you enlarge it? Oh. See here, you are saying that you are N1, P, they are replaced by N1 tilde and P tilde, saying that you have introduced fuzzy in those two things, right?
Yes, sir.
But what is your N1? In the previous slide, you are mentioned your definition of N1. Can you go to that?
So sample size.
Yeah, it is the size of the first sample. Is it not a, see, how come fuzzy enter into a sample size? That's my question. Even if it is something like small p, okay, maybe we can accept with some observational errors and other things. Okay, but when it comes to first stage sample size N1, okay, is it reasonable that you can take it as fuzzy?
So there may be a possibility.
No, we are going to fix the value. Okay, so if your N1 is 3, this is what is going to happen. If P is equal to 0.5, this is going to happen. So that's how we are going to proceed with N1, N2, and with probably R1 and R2. And for that, you are going to find probability of acceptance and all the curves, rest of the things. So you may have some fuzziness attached with certain parameters, but is it okay to assume considering the sample size itself? So that's one thing. That's one thing, and you should, as Professor was mentioning, you should have justified that fuzziness, how it enters into the structure, okay, that would have been better. But still, you have some thought over it. Okay, so where to assume person, okay, and where not. So I think that will be somewhat useful, because all variables need not be fuzzy. All variables need not be fuzzy. There are certain variables which give scope for making it as fuzzy and doing fuzzy operations and optimizing and other things. Okay, I think, but for that, I think other things are very good. We can congratulate the presenter. Thank you, madam.
Thank you.
I think now Jayakudi can proceed.
Yes, sir. Yes, sir. Good afternoon to one and all present here. This is Jayakudi doing research work in Presidency College, Department of Statistics, under the guidance of Dr. N. Sundaram. Today, I'm going to present the paper entitled on Statistical Inference on Competing Risk Models. This is an abstract of our study. In survival or medical studies, it was more interesting to study separately death due to different causes of failure rather than combining all the causes. So in this paper, we made an attempt for statistical inference on competing risk model using non-parametric, semi-parametric, and parametric regression model, a set of simulated competing risk data with a different sample sizes 50, 100, 150, with a different censoring percentage, 10%, 20% have been used for this study based on Bartwell and Weibull distribution model. The parameters are estimated using maximum likelihood approach, and the relative risk for each of the cause of failure was observed, and the validity of the model is assessed using AIC and BIC values. Next. Aim and objective of our study. So our aim is to analyze the non-parametric, semi-parametric, and parametric competing risk model for the set of simulated data based on Bartwell and Weibull model, and comparison was made to find the best model. So generally, a competing risk arises in medical or reliability study when there is more than one possible outcome during the follow-up period in the study. So the beauty of the competing risk model is that the occurrence of outcome of interest precludes by another event of interest. For example, in a cancer-related study, death due to cancer, it is our primary interest, but death caused by other than cancer is a typical example for competing risk model. So the interesting point of the competing risk model is to study on the distribution of time to failure from one risk in the presence of all other risks. Next slide. Methodology. Generally, the competing risk data is represented as a pair of t comma delta, where t is the failure time and delta is the indicator variable. Delta takes the value 0 for the censored observation and delta equal to 1, 2, and so up to k, depending on the number of competing event we have. And in this paper, we studied all the three approaches, that is non-parametric method based on cumulative incidence function, semi-parametric method dealt with cause-specific hazard and subdistributional hazard. In parametric method, we use the likelihood function and study the estimate using MLE algorithm. In non-parametric, cumulative incidence function is estimated through the Kaplan-Meier estimate. So 1 minus of Kaplan-Meier estimate give the cumulative incidence function, and it is calculated integral of 0 to 1 S of u HK of u du. The cumulative incidence function has no one-to-one link to the hazard rate and then cumulative incidence function of the event of interest. So basically, the Kaplan-Meier estimate give a biased estimate in a case of competing risk because it considers the competing event as a censored. So it always overestimate in most of the case. So the cumulative incidence function is studied using the function cumin in our program. Next slide, sir. Semi-parametric approach. In semi-parametric method, we have two approaches. One is cause-specific hazard, and the next one is subdistributional hazard. In cause-specific hazard, we study the hazard rate for each cause of event by considering the other causes as censored. So the cause-specific hazard function is nothing but the instantaneous rate of the occurrence of the kth event in the subject who are currently event-free. So to study the effect of covariate in cause-specific hazard using Cox proportional regression, the COX-PH function used in survival package to study the cause-specific hazard. Next slide, sir. Subdistributional hazard. Subdistributional hazard method is also known as fine grained model. So it is a Cox proportional regression, but the cumulative function is associated with it. So directly the covariates are directly connected to the cumulative incidence functions of the interest. That is lambda ij of t equal to ext of beta j dash xj lambda naught of j, where lambda naught is a baseline subdistributional hazard function, and this is studied using CRR function in R. Next, parametric competing risk model. To analyze the parametric competing risk model, two causes of failure is discussed here. The likelihood function to be considered for k equal to 1 for the desired event and k equal to 2 for the competing event. So the survival function is factored into the product of two cause specific survival function. So S of t comma pi is equal to survival function for the desired event multiplied with survival function for the competing event. The corresponding log likelihood is written as L of pi 1 comma pi 2 equal to the product of density function for the desired event multiplied with survival function for the competing event to the power of delta I1. Then density function for the competing event and survival function for the desired event to the product of delta I2, delta 2i, and then the product of two survival function to the power of 1 minus delta 1i minus delta 2i. And then to study the covariate effect, we define the scale parameter beta j through the linear combination of the covariate. That is beta j equal to exp of neta naught j plus neta 1j plus x1j plus neta 2j, x2j, and so on up to how many variable covariate we have that was included in the model. Next slide, sir. Relative risk. One of the important aspect of competing risk to study the relative risk of the competing risk in the presence one risk in the presence of all other risks, and it was achieved through the equation integral of 0 to infinity hj of t to the product of survival SL of t, and then pi 2 is equal to 1 minus pi 1. So in a case of variable distribution, the shape parameter beta considering to be the equal, so beta 1 equal to beta 2 equal to beta, and the corresponding relative risk is given by pi 1 is equal to alpha 1 by alpha 1 plus alpha 2, and pi 2 is equal to 1 minus pi 1. Simulation procedure. To investigate the practical aspect of the probability task and applicability of constructing these models, a simulation study was carried out based on the following procedure. We generate two random sample xij, that is for the Bartual model. xi1 is equal to Bartual of alpha 1 comma beta 1, and xi2 equal to Bartual of alpha 2 comma beta 2. In the case of variable model, so xij follows variable of alpha j comma beta j. So after generating these two random variables, we find the failure time, that is survival time ti is equal to minimum of xi1 comma xi2. After finding the failure time, the respective sensor the status has been generated by defining the respective probabilities value, which was explained by undemanding simulation approach by Ponnaraja ETL in 2014. And also we add on package of Kruka ETL for used to generate the random sample used to generate the data for Bartual and variable competing risk model with a different sample sizes 50, 100, 150 with a different censoring percentage 10% and 20%, and the covariates are taken to be gender 0 for male and 1 for female, and the x1 is an exponential random variable and x2 is a uniform random variable. Result and conclusion. From the result of the cumulative incidence function, we estimate different cause of failure, and the corresponding comparison between the gender has been made presented in this table. So with a chi-square value and the respective probabilities value, so it is shows that the male patients have more likely to die from competing risk than female patient with a probability 0.02 and 0.19, and the respective cumulative incidence function shown in the next slide. Next slide. So this is a cumulative incidence function for the variable per model with a sample of size 50 with a censoring percentage 10% and 20%. Next slide, sir. The result for the semi-parametric approach. So in this case, we have two methods, cause-specific hazard and subdistributional hazard. So both the method gave the same result as well as when comparing the models, Burr model and Weibull model, more or less they both are same, but when comparing to the likelihood, the Weibull model has little bit lower when compared to the Burr model. As also indicate that the sample sizes increases, the parameter has been increased and the standard error will be decreased, and the variable x1 has more significant in most of the cases of different sample sizes. Next slide, sir. So the same result also get for the 20% of censoring observation. So, but it is better to have a less censoring percentage in your data, because in competing risk model, we are studying one risk by making the other risk to be censored. So already there's one sensor observation, and making the other risk to be a sensor, the censoring percentage will be increased. So it is better to have lower censoring percentage in your data. The fit is good. Next slide, sir. So this for the parametric competing risk model, without allowing the covariate, the study was made for all the sample sizes with the censoring percentage, and AIC, BIC value is calculated, and the relative risk is also calculated. This is also shows that the Weibull model gave a good fit. When allowing the covariate, the X1 is a exponential random variable, shows the effect in both the censoring percentages as well as the sample size. Next slide, sir. So conclusion, this paper concludes the statistical inference on competing risk model using non-parametric, semi-parametric and parametric regression model to check the key status of the model. Simulation study was carried out using R software. Based on the cumulative incidence function, we found the CIF curve and then the chi-square probability value, and some significant group classification was identified. In semi-parametric method, both the cause-specific and subdistributional hazard values has been calculated, and the variable entered here is the exponential random variable, shows significant effect in most of the cases. And when compared to the pseudo likelihood ratio value, Weibull distribution is gave good fit than Bartwell distribution. The same case for the parametric distribution, maximum likelihood estimate has been used to estimate the parameter values. As we know that the sample size increases, the standard error of the parameter will be decreased. That is also achieved in our model. Also, the variable entered there is also the exponential random variable. So hence, the Weibull distribution gave the good fit than Bartwell distribution in our case. Thank you, sir.
Yeah, very authentic presentation. So any questions?
Can I ask one clarification, Vishwanathan?
Yeah,
a nice presentation, Mrs. J. Cody.
Thank you, sir.
My general, I've seen this, all the presentation, when you're doing the simulation, you're just restricting to the sample size 50 or 100. Why? Because when you're doing the samples simulation, you can go with the larger sample size to estimate these parameters. That's my first question. Go ahead.
In a case of a survival data, we can't get a large number of sample data. Only it is will get 50 or 100 or 150. So it is very complicated to get this type of data in real life. So our model, we always use the less sample size.
Could you give us an example of real life data where you will get only a limited sample size?
So in a case of a transplant study, sir, only the few people did the transplant. So we can't, if you take a cancer data, we have a large number of data we can have. But in a case of a transplant, kidney transplant or heart transplant, then the sample size is very limited. The availability of the data was very limited in that case.
Oh, okay. I got it. Yeah. Right. Thanks. But I know you're restricting your rare disease or transplant patients, but nowadays there are a lot of transplants happening all over India. If you take government of Ministry of Health record, you can see how many transplant surgery is happening in every year. So that is one point. Another one is in a breast cancer or a colon cancer. It's a lot. and you should try to run it with a larger sample size when you're doing the simulation studies.
Okay, sir. Sure, sir.
That's my one suggestion,
Okay, sir. I'll do.
Thank you.
Thank you, sir. Thank you.
Yeah. If there is no other question, I think we can call upon the next candidate. Congrats, Taikudi. It's a good presentation. Yeah, please proceed.
Good afternoon to one all present here. I am Ghosh Bhaskar, Research Scholar of Statistics, University of Madras. The topic is reverse Kaplan-Meier technique using weight function. Next slide. Introduction. Survey analysis is a collection of statistical techniques for analyzing positive value random variable, which represents the lifetime, time taken to attain the endpoint in any experiments. The data arise from various fields, including medicine, engineering, demography, etc. This survival time is also a positive random variable, which measures the time from a well-defined time origin until the occurrence of a particular event of interest or endpoint. It can be measured in years, months, weeks, days, hours, etc. Next slide. In survey analysis, the dataset can be either complete or censored. That is, the complete data means the precise time until the occurrence of event of interest is known. In most of the situations, the survival times are frequently censored. Survival time for an individual is said to be censored when the endpoint or variable of interest could not be observed exactly for that individual. These are types of censoring. I used to skip this. Next slide. The next is Kaplan-Meier estimator. The celebrated Kaplan-Meier estimator, also known as the product limit estimator, which estimates the survival probability for the lifetime data, is defined as S hat of T is nothing but product of J equal to 1 to K, Nj by Dj by Nj, where Nj is nothing but number of individuals who are under risk just before time Tj. Dj is number of individuals who have attained the event of interest at time Tj, and Cj is number of individuals who could not attain the event of interest at time Tj. Follow-up time is more important in the field of survival study, especially in clinical trials, since unequal follow-up fails give accuracy and therefore will lead to biased results. Observations with many early events in a lengthy study period would not be appropriate to have a long median follow-up time, and so the Kaplan-Meier estimate will not be reliable, especially for the prolonged time study. In some survival studies, majority of the individuals attain the event of interest in the start of the study, which makes the estimated median survival time as less potential. The enhanced way of looking at median survival time is the potential median survival time, which can be obtained by switching the status indicator so that the complete observation can be observed as censored observation, with the implication that the observation time would have been much lengthier had the event not occurred. So this method of estimation is nothing but reverse Kaplan-Meier estimator has been used to assess the length as well as the completeness of the follow-up, which is obtained by switching the status indicator. Next slide. The reverse Kaplan-Meier estimate of survival function is the same as the traditional Kaplan-Meier estimator of survival function, by just reversing the status indicator. So though it is same as the Kaplan-Meier estimator, just the difference is status has been reversed. So it's DJ star nothing but number of individuals who attain the event of its interest, but as per original, it is not attained, it has been censored. Next slide. Limitations in the reverse Kaplan-Meier estimator. An important limitation to the reverse Kaplan-Meier estimator is that it removes the event of interest developed during study from all subsequent research. Also, it is to be noted that whenever the event observation is considered as censored observation, then the reverse Kaplan-Meier overestimates the survival function due to the presence of censoring. In this study, the authors proposed a method in the place of existing reverse Kaplan-Meier technique by giving the proper weightage for the complete and incomplete observations. This is the proposed weight designed by counting the percentage of event and censored observation to the total number of risk. That is nothing but 1 minus average of dj star by n, comma cj star by n, where n is the total number of risk for individuals in the data set. And therefore, the reverse weighted Kaplan-Meier estimate nothing but S hat of T is equal to product of Wj into Nj minus Dj divided by Nj. Reverse weighted Kaplan-Meier estimate shows better results when the standard error of survival function are obtained based on Kaplan-Meier, reverse Kaplan-Meier, and the reverse weighted Kaplan-Meier. And standard error is given using Greenwood's formula, and a 95 confidence is also given. Next slide. Applications for our study. 2 existing datasets have been considered and analyzed in order to claim the proposed method, that is the reverse weighted Kaplan-Meier, to obtain potential median survival time from Kaplan-Meier and reverse Kaplan-Meier. And further, standard error and confidence have also been obtained by following respective graphs for the 2 datasets. Details of 2 datasets are the IUD data taken from the college book, which has 50% of censored observation, and next is the heart transplant data, which has 27% of censored observations. Next slide. So this is a data set 1, this IUD data. We have we have obtained for all the data, that is, we have obtained the reverse weighted Kaplan-Meier, and it shows that it shows better survival probability than the reverse Kaplan-Meier estimate. Next slide. Similarly, it has been obtained for the heart transplant data. Next slide. And we have obtained the standard and confident intervals for IUD data as well as for standard heart transplant data. Next slide. Next slide. This is a graphical representation of survival probabilities. Before slide. From this, it shows that the red one is the original Kaplan-Meier estimator, the green one is the reverse Kaplan-Meier estimator, and the blue one is the proposed method. And we can see due to the 50% of censoring, the reverse Kaplan-Meier shows better survival curve than the Kaplan-Meier and the reverse Kaplan-Meier. Next slide. And this is the heart transplant data. You can see for the red one has 27% of censoring, but if you use the reverse Kaplan-Meier estimation, the 27% of censoring will become a 73% of censoring. In that, the survival probability will overestimate. It will be overestimated the survival probabilities. Therefore, to appropriate it, reverse Kaplan-Meier, weighted reverse Kaplan-Meier has been obtained. Next. Illustration. In this study, 3 scenario has been illustrated. That is, majority of events and censored observation attained at the start of the study, or the majority events and censored observations attained at the middle of the study, or the measure of events and censored observation attained at the tail of the experiments. This survival probability has been obtained by using Kaplan-Meier reverse and weighted reverse Kaplan-Meier estimator for the above 3 scenarios. And the analysis of this method has been done using R software. Next slide. So we have 3 scenarios. Assume that at the start of this time interval, many events have occurred. That is, you can see the scenario A. From the start of the experiment, if you have majority of individuals have been event or censored. Next scenario is in the middle of the study, if majority of events have been event or censored. Scenario C, the events have been occurred at the tail of the experiment. Next slide. So we have used two, that is small sample size and large sample sizes. Small sample size, it has been shown that it is just near to the reverse Kaplan-Meier estimator. It is between the Kaplan-Meier and the reverse Kaplan-Meier estimator. And for this scenario B, it is in the middle. That is, the majority of events are in the middle. And next slide is scenario C. Similarly, for the large sample size, next slide. You can see that for the red one, due to the early many events for scenario A, that is for larger events, you will get the median survival time will occur very soon. For that, the information will get lost. For that, the information will get lost. So therefore, you can see that after using reverse Kaplan-Meier technique, due to this higher amount of censoring, it will get overestimated. So we need to contribute the weight for the complete observation as well as for the censored observation. For that, we have used the average weight and we have obtained the reverse weighted Kaplan-Meier estimator. Next slide. Similarly, for the scenario B as well as for the scenario C. Next slide. Conclusion. Tables 1 and 2 shows that the proposed method, namely reverse weighted Kaplan-Meier estimator, gives a better survival estimate than the Kaplan-Meier and reverse Kaplan-Meier, as the reverse weighted Kaplan-Meier has better standard errors and confidence intervals. It is also observed that the reverse weighted Kaplan-Meier method performs better than the existing methods in the sense giving appropriate weightage for both complete and censored observations occur in each time interval, more particularly for the 3 scenarios. The survival curves of the reverse Kaplan-Meier given in figures 1, 2, and 3 shows that it overestimates the survival probabilities. Hence, it gives the biased information due to the reverse status indicator. The proposed method, reverse weighted Kaplan-Meier estimate, shows better estimate by obtaining potential median survival time when it compared with the other 2 existing methods. It is inferred that the weight assigned for reverse weighted Kaplan-Meier method is appropriate to use whenever the majority of individuals occur in the survival studies. These are my reference.
Yes. Nice presentation. Any questions from the audience? Okay.
Sir, good evening, sir. I am Divagar from Bardiyar University, sir.
Yeah, please.
I want to know small things, sir.
Yeah, please.
You have used some of the Kaplan-Meier estimator method for small sample size data on large data set. You also compared which software you used for draw the graph?
R software, sir. By using creating own function, yes, sir.
Okay, okay, sir. Okay. Thank you.
Yes, thank you.
Any other question? Yeah,
Vishwanathan,
please.
I just want to give a comment on that.
Yeah.
Mr. Ghosh, it's an excellent presentation and also nice to see the differences between the Kaplan-Meier as well as the reverse as well as the weighted Kaplan-Meier. It's a wonderful research, I think. And also, my only one clarification, you're going to use the same set of data to show the survival probability between these three modelings, or could you enlighten with the, because when I have a set of data, if I see someone sees that as a clinician, if I see that, okay, if I use the reverse Kaplan-Meier model, my survival probability is this, meaning that at 20 days or 20 years, I see that up to 45% is survived as compared to the Kaplan-Meier at 20 years, only 20% is survived. So how do you distinguish this two in a same set of data?
It is depends upon the survival data. Suppose it is based upon the scenario. For example, based upon the earlier study, if many events happen, like for example in clinical trials, you will do many testing, and sometimes based upon the experiments, many people die. So the median follow-up will become very early. So we don't know how to get the potential median for that. So because of that, for any large data set or small data set, if you reverse it, the reverse Kaplan-Meier estimate will obtain. But we don't know how the events and censored observations occurs, because they both occur simultaneously. When we reverse it, the median, the event occurred will change to censored observation, and so the censored event will automatically transfer to event observation, so that we don't know the precise information what we have get in the data set. For that, I have used this weight.
Okay, yeah, it's a nice presentation. The only thing I couldn't get it is reversing of what? Reversing of the data you have? Reversing the event which has happened?
Reversing the status, sir. That is, the death becomes the censored and censored becomes the death. Event becomes censored and censored becomes complete observation.
But, okay, great.
Yeah, I too have a comment in the sense that applying the same data when applied with two different methods, if you have two estimates, which one is to believe? Okay, so that problem is what precisely Dr. Bala is asking. So
Yeah.
which method do you take?
Yeah, because you are modeling on the death for the Kaplan-Meier. Yes, and the reverse Kaplan-Meier, you are modeling on the survival of people. So how does it comparable? Right?
Yes, sir. But for example, due to suppose the majority of individuals attained early, that is based upon the experiment time, if the events occurred earlier enough, then reverse Kaplan-Meier will be used to predict the potential median survival time for that particular data set. That is a scenario. That is a scenario we have used, sir.
Yeah, that's correct. But think about in a real life scenario,
yes,
Mr. Ghosh.
Yes, sir.
Event is occurred after 10 years. You are following the patient for 10 years in a cancer trial.
Okay,
right?
Sir. Yes, sir.
And the median survival is 5.5 years, right?
Okay, sir.
And you are modeling for the Kaplan-Meier on the event occurred. You are censoring the subject at the time of the event happened.
Yes, sir.
And you are reversing that event for those who are surviving, not on the death.
Yes, yes.
That's what my
yes, that is the scenario. That is the reason only we have used the weighted function, because if it's the death even becomes censored, then predicting the probability will become a problem based upon the weightage given. That's why we have given weight combination for event as well as for censored observation. That's why we are giving an average for the weight as well as censored, so that it goes in a smooth way. We can't predict, but because if death becomes censored means then the Kaplan will get overestimated because of censoring. Because of that, we have given a weight to obtain a potential median, so the lifetime of the data set.
Good explanation. So are you an MPhil student or PhD?
I'm a research scholar, yes. Research scholar.
PhD, you're doing PhD.
Yes, sir. Yes, sir.
Good work. Thank you.
Thank you, sir. Thank you, sir.
Yeah, congrats those, and we'll move to the next candidate. And I think we are running out of time, so the other candidates stick on to their time and try to complete as soon as possible.
Good afternoon, everyone.
Yeah, please proceed, madam.
Yes, good afternoon, everyone. My name is Radha Lakshmi Kain from the Department of Statistics. So today my presentation is on identification of outliers, a case for applying non-mesocratic normal distributions. So this is a part of my research work under the guidance of Dr. Martin Luther William. So coming to introduction and motivation. So normal distribution and its properties are so beautifully crafted that we all statisticians are always glued to it. But in real time, the mathematical conveniences in the normal distribution might not help in the analysis because it might result in sacrificing the information that would otherwise be drawn from the data. So our research aims in applying non-mesocratic normal distribution to a real-time data for identifying the outliers in comparison with normal distributions. The references for the application has been made on a recently developed class of non-mesocratic normal distributions by Radha Lakshmi and William. Next slide. So according to a review of literature, according to the recently developed paper, we consider a random variable R, where R square follows a chi-square distribution with m degrees of freedom and U be uniformly distributed in the interval -1 to 1. Also, U and R are independent. Therefore, a random variable following a non-mesocratic normal distribution is defined as x is equal to R lambda U, where lambda square is given this definition, variance of x by expectation of R square into expectation of U square. Now, the kurtosis beta 2 of x is given by the formula 9 by 5 into m plus 2 by m. Now, there are some special cases wherein if you substitute m is equal to 1, beta 2 of x comes to be 5.4. When m is equal to 2, it is 3.6. And when m is equal to 3, the kurtosis is m is 3. And when m is equal to 4, beta 2 of x is 2.7. So some observations from the previous slide is that when m is equal to 1 and 2, the distribution of x is leptokurtic. That is, the kurtosis value is greater than 3. When m is equal to 3, we get the kurtosis value to be 3. For higher values of m, the kurtosis values go below 3. And also, asymptotically, we see that the kurtosis value approaches 1.8. Now, the class of non-mesocratic normal distribution encompasses a wide class of distributions with moment-based kurtosis values ranging from 1.8 to 5.4. The density function of the random variable x, which follows univariate non-mesocratic normal distribution, is given by the below expression. Now it is observed that if we substitute m is equal to 3, the density function reduces to that of a normal random variable with mean 0 and variance lambda square. Also, the density curve has points of inflection at plus and minus lambda into square root of m minus 2. And if we substitute m is equal to 3, the points of inflection are plus and minus lambda, which is nothing but the standard deviation of a standard normal distribution. Also, the estimation of the parameters mu, lambda square, and m are obtained by the method of moments, and they are given below in the following 3 equations. Next slide. Having given the brief review of the literature, we have used this distribution in applying to a weather data for identifying the outliers. And for this purpose, we have taken the weather of Chennai from the period 2012 to 2019. And in particular, we have taken the observations to be temperatures between the time 4 a.m. and 7 a.m. from 20th December to 22nd March of the consecutive year. And we have applied Shapiro-Wilks normality test, and we have got the p-value to be 5.85 e minus 0.08. So it denotes that the data is not normal. And also, when you calculate the kurtosis of the data, it is seen that it is 2.7. It indicates that the data is platykurtic in nature. Now, using the estimation procedure, we have found out that the estimate for the parameter m is 4. So we have tried to tabulate the quantiles for the same. And now we have tried a non-parametric test, Kolmogorov-Smirnov test, to see the goodness of it, and we see that the data points are accepted at 1% level of significance. And also the quantile of order 0.4986 corresponds to the point 2.69. These are the snippet of the half CDF values for the parameter m is equal to 4. Next slide. Now I have two graphs wherein I compare, as my objective is to identify the outliers. I can see that when I apply the 2.69 control limits, there are two outliers which are detected for the dates 8th and 9th of March, which indicates a spike in the temperature. Similarly, in the next slide, in this slide, we can see that if I am using the normal control limits, that is the 3 sigma limits, I can see that there are no outliers detected. So this is what I wanted to conclude. There is a comparison wherein the norm, when you assume that the data follows normal distribution, the outliers can sometimes be neglected. So it is better that we go to a distribution which aptly fits the data. So we have considered here the kurtosis as an important parameter. And these are my references. Thank you.
Yeah, nice presentation. And any questions from the audience?
Can I ask a question, Vishnu?
Please, sir.
Yeah, the nice set of data, 2012 to some 9 years or say. So you're trying to find out the normality of the data. And once you look into the data of those outliers, are you going to remove the outliers and going to fit the model again, or you are going to keep the outliers in the data and smoothen it?
Sir, I think avoiding the outliers would be again going back to normality and going for that conventional procedure. But I would like to keep the data and try to proceed with the smoothing of the data. That is what I would prefer to. But this is my research work, and we are in the process of finding some testing procedures so that it can be further carried on.
Okay,
But,
and one point you mentioned that one of the year you noticed that the peak happened in March 8th or 9th, something you mentioned that.
Yes,
is that
sir.
similar? Is that similar across the different years, or it's happened only 1 year?
It has happened only 1 year, sir.
Okay, so the remaining years are not, you have not seen that type of fluctuation in the data.
No, sir, there has been no pattern or cycle representing. It is just in these 2 dates of the whole data that we have seen the spike happening, and it has been captured.
Okay, do you know the reason why the spike has happened?
Actually, March 4th of 2019 has been Mahashivaratri. So scientifically, it is said that it would mark the onset of spring and summer. So there would have been some spike in the temperature, and during the dates of 8th and 9th of March, there would have been an increase in the temperature, and it had been those 2 days. That is what I feel so.
Nope.
Would have been the reason.
Maybe it's a good explanation. Thank you.
Welcome, sir.
Any other question? Yeah, we accept that the justification is more close to a real world scenario, and probably the other question proposed by Professor Bala, whether to keep the outlier in the model or to detach it from the thing. I think it has now becoming more philosophical rather than statistical. Because in both ways, I think if you drop the outlier, it's that we are going to model for a partial data, And if you are going to accommodate it, naturally it is going to deviate the parameter estimates. So I think that's a $1 billion question, so to say. And it's a nice presentation. Thank you, madam. We will proceed to the next candidate.
Dr.
Thank you, sir.
Swanathan.
Yeah, please.
Dr. Swanathan, may I intervene for just about
Yeah.
half a minute?
Yeah, please, Professor.
Yeah,
Please proceed.
thank you, Dr. Adharashmi. Congratulations on your nice presentation. Actually, she is under my guidance doing PhD. Dr. Sunathan, in another work, in fact, I wanted to present that work in this conference, but then I decided to present the non-parametric discriminant analysis this morning. In one of the projects that we did, we introduced a totally distribution-free approach for outlier identification, which was like a step-by-step process of identifying outliers. And what we found was, in fact, that was a very nice research done with one of my MSc students about one and a half years ago. So what we found was, once we remove the outliers, maybe about 3 or 4 outliers were removed one by one on a step-by-step basis, and we found that as a net effect of this removal of outliers, whatever model we built, it really improved quite very well significantly. And that was a very interesting observation in that particular research that we did. In fact, I wanted to make a presentation on that. Maybe some other there may be some other time where I could make it. Sure. It is an interesting approach, totally distribution-free approach. Outlier identification is definitely should lead to a situation where these outliers are removed for any further analysis, because these are going to play a spoil sport in further modeling.
Yeah, accepted, Professor.
Thank you.
Can I comment on that?
Yeah, please, Professor.
Yes, sir.
Quickly. Mr. Martin, that's
Yes.
Good one, but you can do a sensitivity analysis by removing those outliers and keeping that outliers in the model and see how the parameter estimates are, whether it is equal, and you can check the standard error of the estimate. If it is close that, then the outlier doesn't have any impact on the outcome. Otherwise, if you see the very wide range of parameter estimates by keeping that and removing it, then you need to seriously think about it, whether removing and keeping the outlier in the model. That's what my suggestion would be.
Okay. Yeah, but what we did was we had a model, multivariate multiple regression model, as a initial model, and then a model after removal of the identified outliers. And what we found ultimately was the model performance was really comparatively very good, far better than the model performance of the original model. So that much we saw. And of course, as you said, there may be we will have to look at the estimates precisely, each parameter estimates and so on. I think that part we have to do.
Yeah. More
Thank you.
Concentration on standard error rather than the parameter itself.
Yeah, correct. The model, what we looked at was the model performance. We looked at the R-squared measure, and we saw how much it had improved, and now the model prediction came out closer to the reality. So that was what we checked actually.
Thank you very much, Professor, for your highlighting comment.
Thank you, Dr. Bala, for Thank you, Dr. Bala. Thank you, Dr. Sunathan. Thank you.
Yeah. I think we have to rush through. We have 2 more candidates left, please.
My humble request, I want to share the screen in my system, sir, because I little bit changed in this slide. With your permission, can I change it, sir? Share it?
Is it possible?
Yes, sir. Yes, sir.
Yeah, then you can proceed. Yeah, you can proceed. You can have your own.
Is my screen visible, sir?
No, not so. Have you shared it?
Yes. The screen.
Yeah, it's coming out now. Your system or possibly your net is too slow, it seems.
Sir, or shall we move to next one, sir?
Yeah, that's better, I think.
Okay, next one.
Yeah. Whether that candidate is available? Ms. G. Prabhavati.
Sir, I
proceed,
think
madam. Please proceed.
so I think Prabhavati madam is not joined the link, sir.
Okay, okay.
Manjula,
Manjula, I think she is coming out of the order.
okay, sir.
Okay, okay, but if she is ready with the things, we can provide some time so that she can quickly complete.
She requested to me, sir. She has attended one meeting at the time.
Okay.
Manjula
okay.
madam. So I think Divagar started sharing his screen, sir.
Okay, okay. Then Divagar, make it quick. Divagar,
Yes, sir.
make
Yes,
it
sir.
quick. Please make it.
Sorry, but
No.
Sorry,
Please proceed.
sorry for the delay, sir. Some technical issues, I could not present the correct time.
Carry on, please. No issues.
So, good evening to everyone. I am K. Divagar. Recently completed my PhD program at Bardiyar University under the guidance of Dr. K.M. Saktiver. I would like to thank to the organized committee for giving me a wonderful opportunity to present my paper to the premier institution, University of Madras, particularly for Dr. S. Suresh sir and Dr. Ramdre sir. Now I am going to present my paper, a study on Population generated diagonal distribution and its properties. And statistical distribution are very useful in describing and predicting the real world phenomena. The right-hand distribution play a vital role in many research areas such as economics, engineering, finance, medical, biological science, and so on. In recently, extension and the generation of the probability distribution are attracted many researchers and statisticians. For example, Marshall-Algin family introduced by Marshall-Algin in the year of 1997, and the exponential family is introduced by Gupta et al. 1988. The exponential family of distribution is provided the flexibility by adding one more parameter to the distribution and has attracted several other. Several classes of distribution have been introduced by adding one more parameter to generate a new distribution in this statistical literature. Here I have mentioned some of the generating family of distribution, namely called Marshall-Algin generating family introduced by Marshall and Algin 1997, exponential generating family introduced by Gupta et al. 1998, quadratic round concentrated map recently introduced by Sean Buck in the year of 2007, Kumarasamy G family introduced by Cardier et al. 2011, and WMG family introduced by Alsomarini et al. in the year of 2016. In probability distribution we can classify it into the two types, discrete distribution and this continuous distribution. In my research, I focused the continuous distribution, namely called diagonal diagonal distribution introduced by Emilio in the year of 1997 for numerical income and wealth data on the size distribution. The diagonal distribution is classified into the two specification, type 1 specification and the type 2 specification. Here I focus the type 1 diagonal distribution for my research work. And the type 1 diagonal distribution has one scale parameter and two shape parameter. It also known as the inverse perturbable distribution, particularly in the actuarial literature. The type 1 diagonal distribution is accommodating with a heavy diagonal distribution. An important characteristic of diagonal distribution is that a Hazard function can be monotonically decreasing and upside down bathed up and then upside down bathed up for studied by the researcher Damma in the year of 2012. This paper we introduce a new generating distribution, namely called Toplian generated diagonal distribution, using the Toplian generic family of distribution studied by Rajai et al. 2016. We have obtained some of mathematical properties and statistical property for Toplian generated diagonal distribution. Here I have done some of the literature work related to my research work. I have mentioned some of the literature work in this slide. Now I move to the diagonal distribution. The PDF and the CDF of the diagonal distribution are given in equation number 1 and 2 respectively. Here we have the three parameter, namely called sigma, theta, and beta always greater than 0, and the random variable x greater than 0. Here sigma is the scale parameter, while the theta and beta are the shape parameter. Recently, Hong and Olidev et al. Studied about the diagonal distribution, namely called exponential Kumarasamy diagonal distribution for income and lifetime data. And subsequently, the Olidev et al. Studied the comma diagonal distribution for income and lifetime data. It is pertinent to note that if sigma is equal to 1, the PDF of diagonal distribution became a healthy distribution. If theta is equal to 1, became a log-logistic distribution. Now I move to the Toplian generic family of distribution introduced by Rajai et al. 2016. This family of distribution introduced from origin from the Toplian distribution. The Toplian distribution introduced by the top and Ligon in the year of 1955. The Toplian generic family for particular which the part of Castle rate and can be used for lifetime modeling. The PDF and the CDF of Toplian generic family of distribution given in equation number 3 and 4 respectively. Here you can see the small f of x and the capital F of x. If you use the small f of x and the capital F of x is the base distribution function of the any distribution. If you use the any classic distribution, we can get the new generation distribution. The corresponding the Hazard function given in equation number 5. Now I move to the proposed model, namely called Toplian generated diagonal distribution, and the PDF and the CDF of Toplian generated diagonal distribution are given in equation number 6 and 7 respectively. Here where sigma is a scale parameter and theta beta are the shape parameter, tau and alpha are the parameter of Toplian generated family of distribution. The Toplian generated diagonal distribution is symbolically denoted by this expression. Here we can see the shape of the PDF for Toplian generated diagonal distribution. Here we fixed the 4 parameter value, and another one parameter is the different value, namely beta 0.5, 1.5, 2.5, 3.5, 4.5. Likewise, we get the different curve. Here, our proposed model probability density function satisfy the base characteristic of the diagonal distribution. It is the heavy diagonal distribution. In our model also is the heavy diagonal distribution. Now I move to the shape of the CDF for Toplian generated diagonal distribution. Our model is satisfy the basic characteristic of the distribution function. The value is increasing from 0 to 1. Subsequently, I have studied the reliability measure, namely called reliability function, hazard rate function, reverse hazard rate function, and cumulative hazard function are given in this slide. Here I have studied the shape of the reliability function for Toplian generated diagonal distribution, and subsequently I have studied the behavior of hazard rate function for my proposed model. And now I move to the statistical property. When we study the new genetic distribution, we want to study about some of the statistical properties. Here I have studied some of the basic statistical property for my model. The orth moment of Toplian generated diagonal distribution given in equation number 12. Subsequently, I got the first 4 moment. The first 4 moment is very useful to find some of the basic characteristic statistical properties of variance, skewness, and kurtosis. Subsequently, I got the moment generative function, characteristic function, cumulative generative function, incomplete moments, and central moments for my model. In this slide, so the expression is shown. Subsequently, I got the conditional moment and the first four conditional moment and the probability moment are the expression shown in this slide. Now I move to the order statistic. In the order statistic is specifically used in the non-parametric statistics. In this situation, I used my model to the order statistics. In the PDF of the PDF of the jth order statistics and the PDF of the smallest order statistics are given in the equation number 21 and 22.2 respectively. Subsequently, I got the PDF of the largest order statistics, median order statistics, and the joint distribution of ith and jth order statistics for my model are given in this equation 23 to 25 respectively. Now I move to the parameter estimation part. Whenever we study the probability distribution, we want to estimate the parameter of the distribution. Here I used the maximum likelihood estimation. In generally statistical literature, we have different statistical estimation method like maximum likelihood method of moments, minimum chi-square, minimum of variance, and least square estimate. Here I consider maximum likelihood estimation method to estimate my model parameter. The log likelihood function is given in equation number 27. And subsequently taking the partial derivative with respect to the parameter alpha, tau, sigma, theta, and beta are given in respectively in equation number 28 to 32 respectively. In the above mentioned nonlinear equation very difficult to solve analytically. In this situation, we can use the nonlinear equation through the iteration method like Newton-Raphson and regular policy method. However, we solve above mentioned nonlinear equation using the R software. Now I move to the application part of my model. In this section, we study.
Can you make it fast because we are running out of time?
Okay, sir. In this section, we study a real-life failure time data set fitting the proposed distribution and compared with other competitive statistical model. The data about the expressed about time to failure 100 centimeter polyester viscose in tactile experiment in order to evaluate tensile fatigue characteristic of the yarn data and its strain level. And this data set recently studied by the Nasiri et al. 2019 for in table number 1 detail about the summary statistic of tensile fatigue characteristics of yarn data set, and table number 2 detailed about the estimated parameter and the information criterion value for a different statistical model, including our proposed model. Here you see the statistical model selection AIC, AICS, and BAC. Basically, the statistical model selection based on the minimum value of AIC, AICC, BAC, and log likelihood. Here you can see that our proposed model provided a very less value compared to other different statistical model, namely exponential generalized exponential diagonal distribution, exponential generalized distribution, and so on. So that we conclude that our model is provided a better fit compared than other statistical model for this particular data set. Now I move to the conclusion part. In this paper, we present a new distribution called Toplian generated diagonal distribution, Toplian generated family of distribution proposed by Rasa et al. 2016. We have obtained various statistical properties like moments, moment generative function, characteristic function, cumulative generative function, inverted moments, central moments, conditional moments, probability weighted moment, and order statistics. We have discussed some of the reliability measures like reliability function, hazard rate function, reverse hazard rate function, and cumulative hazard function through the graphical representation. The proposed model parameter are estimated by the method of maximal likelihood estimate method. Finally, we have used a real lifetime data set to fit the proposed model distribution. It is seen that the proposed model has more flexibility compared to other models. These are my reference. Thank you.
Yeah, I think you have done all possible things with the given distribution. Any questions from the audience? Okay.
Viswanathan,
yeah.
Professor Viswanathan.
Yeah, please.
Now I would like to give one suggestion.
Yeah.
In MLE, you have used that logarithmic differentiation, right?
Yes, sir.
Right. This logarithmic differentiation, I tell you, there is one method which has not been taught at the +1, +2 or undergraduate level. This is the technique due to Feynman. FEYMAN.
Richard Feynman.
Richard Feynman. Feynman differentiation and Feynman integration, one has to learn that in statistics students, it will be very helpful to evaluate MLE. Even single stroke, you will get the differentiation. You need not go to, I don't know how you differentiated that huge expression. This type of huge expression, using that Feynman differentiation in single line, you can get the answer. Okay, I can try to educate this Feynman differentiation and integration for all our statistics students. It will be very, very useful. Okay, this is only my suggestion. I think you know send so many days to differentiate and then get the final expression. But in half an hour, you can get the entire thing. Or you might use the software to get the differentiation, because there are Mathematica, other softwares are available. Maple softwares are available to find out the differentiation, because now it makes our students very lazy even to find out the differentiation.
Thank you, sir. Thank you for.
Yeah, it's a wonderful addition to the thing, because as Professor was mentioning, Richard Feynman was a Nobel laureate, and he was very much associated with the Manhattan Project in USA, with the development of atom bomb at that period of time, and he shot into fame like anything. And as Professor was mentioning, there was a separate school of teaching using Feynman methodology. I think everybody should follow these shortcut methods. I don't know whether it's a shortcut method or anything, but it's a very useful.
Straightforward.
We cannot use the word shortcut.
Yeah.
Because K. Balasubramaniam, our statistics professor, he used to say longer or lengthier proof is the evidence of our ignorance. So whenever it is short, okay, it seems we are very crisp and intelligent.
Yeah.
Okay, thank you, Professor. Thanks for your comments.
Thank you, sir. Thank you for your suggestion.
Next candidate.
The next one.
Sir, am I audible, sir?
Audible, madam, please proceed.
Yes, sir. So good evening to one and all present here. I'm Shweta, research scholar from Madras Christian College, Department of Statistics. So today I'm going to present a paper on the topic effect of electronic payment acceptance in the case of small vendors. So this is the outline of my study. Moving on to the introduction part, we all know that marketing area has a very high volume of money transaction, which is merely through cash. So now at present, one of the developing payment methods adopted by merchants is in the sector is electronic payment. This has increased tremendously after demonetization. So the whole isometrics of moving from cash-driven economy to cashless economy has somehow been assorted with demonetization that was aimed to extract liquidity to exhibit the black money. And with the growing adoption of electronic payment, there is an increasing demand for faster payment services, which will facilitate ease in doing financial transactions. And according to the government of India, this cashless plan will increase employment, reduce cash-related corruptions and theft, which will obviously attract the foreign investors to the country. And India has been using the electronic payment for more than many years now, but still there is a major obstacle for the adoption of cashless payment mode. Why? Because it is the point of sale terminals works as the mobile internet connection. Next slide. Now coming on to the review of literature, these are the three papers which I have referred. Objectives. The main objective is to know the effect of demonetization as well as the influence of introduction, how the effect of introduction electronic payment bank services of financial inclusion, and also to produce knowledge how consumer cope with any negative effects of demonetization and effect of cashless payment, to know the impact of note ban decision on the Indian economy and cashless payment. From this study, it will be helpful for the citizens of India, Indian government and businessmen to know about the future condition of economy, Any businessman can take a wise decision so that they'll be able to generate more revenue and can earn the profit in the actual market scenario. Now, coming on to the data collection part, in this study, we have collected the data from secondary sources, and further related data of the study were taken from the research articles, journals, and magazines. Now, coming on to the analysis part, here the data analysis was done using SPSS. Factor analysis and K-means algorithm are the statistical tools that were used to analyze the data. Here we have the null hypothesis to be the factor analysis under study is invalid. So on testing the above hypothesis, we get a tabular column which has KMO and Bartlett's test. So from this, you can see the measure of sampling adequacy to be 0.870, which is very useful. And also we have the significant value to be 0.00, which is less than 0.05. And hence we reject the null hypothesis. And so on. We have moved to the further calculations. Here you can see with reference to various factors, digital literacy factor allocated in the first factor that accounts for nearly 42% of the total variation. Then the impact of demonetization are heavily loaded in the second factor, accounting for about 12.42% of total variation. And the third factor comprised of impact of RTGS and NEFT transaction. It has about 10% of the total variation. So from this, we have finally concluded that the variables, various variables which are included for study are explained by these three factors depending on their priority and the amount of variation they have among the total variation. And these are the factors that are responsible for the impact of cashless payment in India during demonetization. Next comes the K-means algorithm. Here from the above table, we can identify the grouping cluster that indicates that the majority of the commuters are belonging to highly affected level. So the only possible reason, digital literacy booths outside bank, majorly in rural areas, facility of mobile ATMs, which can enhance the limit of removal of service tax charge and also increase in daily cash withdrawal limits from ATMs. Now coming on to the suggestion and conclusion. Based on the analysis, we have found that the government need to set up digital literacy booths outside the bank, majorly in rural region. Also, government should print more smaller denominations such as 50, 100 and 500 notes so that there will be sufficient circulation of money in the market. Government also should ensure that the sufficient quantity of money is being transported to the banks, both in rural and urban areas on time. And the facility of mobile ATM in the government, both in public and private corporate sectors. Government has to encourage digital transfers such as RTGS and NEFT in order to adopt the available facility and also to make people less dependent on cash transaction. And finally, I would like to conclude by saying that though the marketers has started moving towards electronic payments, to some extent, the whole marketing sector is yet to pick up card and other electronic payment methods as one of the most secure and convenient mode of cashless payment in retail marketing. So these are the papers which I have referred for the study. And I would like to thank everyone for giving me this wonderful opportunity. Thank you, sir.
Yeah, a nice presentation. And any questions from the audience?
Vishwanathan, can I ask for a
please.
clarification? Yeah, it is interesting to know that demonetization and the effect of transactions are good, and India is acquiring more and more internet facilities all over the country. But in the beginning of the slide, the presenter mentioned that the objective is the effect of demonetization and the impact of electronic payment. I was thinking about something, if you are having that type of an objective hypothesis, and there should be some kind of a modeling, there is an outcome, but she suddenly jumped into a different arena of doing the cluster analysis and K-means cluster analysis, having a set of variables and finding out important variables from that. That's what there is a disconnect. I don't know whether am I missing something in this presentation or something is not clear to me. That's what my take on that.
Sir, I was about to do furthermore analysis, but since I couldn't find much time, since I have a 2-month-old baby, but that is not a excuse that I have to give, but I am doing my best in my further project, sir.
No, I'm not discouraging Mrs. Shweta.
Yes, sir, I can
What I'm
understand.
trying to say is the data is rich. You did a wonderful job, and it's a very informative.
இது என்ன பண்ணினா அதுக்கு சொல்லு முன்னாடி இது இது இந்த 54
the organizers mute the other
இது plus 3 வந்து எவ்வளவு 39 plus 15 is equal to 39 49 54 ன்னு சொன்னியா இப்போ இது மேல இருக்கிறது
please.
So Shweta,
yes sir, yes sir.
my suggestion is this is wonderful information and wonderful data you acquired. The only thing, the disconnect what I see is, please think about it.
Yes sir, yes sir, I can understand, sir. I can understand your point,
yeah,
sir.
That's the only thing. Otherwise, it's a good work. Congratulations.
Yes, thank you so very much, sir. Thank you, sir.
Sir, please unmute, sir.
Sorry. My question is about your suggestion of increasing smaller denominations. How
Yes,
come? Yeah. How come you arrive at? Is it a data driven or is it a suggestion?
Sir, it's just a suggestion, sir.
Oh, it's not based on any outcome of your data analysis.
No, sir, no, sir.
Okay, but then it is beyond question. Okay.
Yes.
I think then congratulations for the presentation, and I think we can move to the next presenter.
Thank you so very much, sir. Thank you, sir.
The last one, sir.
Yeah, okay.
Am I audible, sir?
Yeah, please carry on, madam.
Good evening, everyone. I am Joy Sharlene, research scholar from PSG College of Arts and Science under the guidance of Dr. G. Uma. My topic is impact of fuzzy logic and its application in medicine. It's a review. So here, the World Health Organization has defined health as a state of complete physical, mental, and social well-being, and not merely the absence of disease or infirmity. Here comes the overview of my presentation. Next slide. Due to time constraints, I'm just giving the review alone. Next slide. Next slide. Yeah, fuzzy logic provides a systematic basis for representation of uncertainty, imprecision, vagueness, and incompleteness. Here, fuzzy logic is in recent years, the method of fuzzy logic, fuzzy expert system, artificial intelligence have largely been used in different areas, including medical applications. So can
yes,
we?
please.
Yeah, okay.
Yeah, proceed.
Yeah, next slide, sir. Yeah, theory of fuzzy. No, before slide. Yeah. What is fuzzy logic? Fuzzy logic is found by the Zade in the year 1965. Fuzzy set was first founded, and next fuzzy logic was founded in the year 1973. Fuzzy logic is a superset of Boolean logic that handles the concept of partially truth, which is truth value between completely true and completely false. Fuzzy reflects how people think. It attempts to model a sense of words, definition making and decision making and common sense, mathematical principles for knowledge representation based on degrees of membership rather than on crisp membership or a classical binary logic. Here is my notation for fuzzy logic. Next slide. Next slide. Yeah, here is a fuzzy set. Fuzzy set is defined in terms of relevant universal set. It is defined as U by a membership function denoted. Formally, membership functions of the form will be between 1 and 2. This is a membership function. Next slide. See, in a crisp set, for example, I have taken a height of a particular person. We can say that he is tall and he's short. Whereas in fuzzy set, we can say that he's extremely tall, he's normal, he's very short, and like that we can define fuzzy. Next. Fuzzy logic can accomplish in two things. Is a of describing human knowledge involving vague concept and enhance ability to develop a cost-effective solution to real world. Next. Fuzzy logic was motivated by two objectives. First, it aims to alleviate difficulties in developing and analyzing, and in second, it is motivated by observing that human reasoning can utilize concepts and knowledge. It is related to artificial intelligence. Next slide. Yeah, in fuzzy logic, we have some linguistic variable. It is a composition of symbolic variables and a numerical variable. We define, for example, I have taken a diabetic patient. I take the diabetic level as X and the ranges as T of X. So in linguistic variable, we use both the values and the variables. Here, components of fuzzy logic. Fuzzy predicates tall, small, kind, expensive, like that. Predicates modifiers as very tall, quiet, more or less, or extremely. Truth values like true, very true, fairly, false. And quantifiers like most, few, almost, usually. And probabilities like likely, very likely, highly. Yeah, this is my membership function for crisp set and fuzzy set. We have 11 built-in membership function in fuzzy. Next slide, sir. Some of my membership functions are triangular membership, trapezoidal, Gaussian, and generalized. In triangle, these are the formulas used in fuzzy, formulas for the membership functions. For triangle, it is very simple and widely used. We have 3 points for forming a triangle. And in trapezoidal, it is very flat top and it is just a truncated triangle curve. And in Gaussian, two-sided composite of two different Gaussian curves with two functions, and bell shape, it is very smooth and concise notations of a asymmetric function. Next slide. Here is just I've taken an example. Consider a statement: do you feel dizzy or giddiness? Is it true if you have only tiredness? We may have a tiredness because of giddiness also. Or is it false if we have a panic attack dizziness? We may get tired because of heavy attack also, heart attack also. Everyone will feel dizziness to some degree. We take it as H and ill to some degree as I. If you feel totally dizziness, then of course H is equal to 1, and whereas here we apply the fuzzy logic as H is equal to 1 and I is equal to 0. Usually everybody has some minor health problem and H is less than 1. That I take that as H is less than 1, but H plus I is equal to 1. In other extent situation, when H is equal to 0 and I is equal to 1, which says that the dizziness is very risky. You are up to date. Sometimes our dizziness may be a cause of death. In case you have only a tiredness, we may write H is equal to 0.999, I is equal to 0.01. If we have side effects of medicines, then we say that I is equal to 0.6 and H is equal to 0.5. In the case of painful attack dizziness, probably we take 0.95 and H is equal to 0.05. Here, diagnosis of diseases using fuzzy. In my references, I have seen many authors have used fuzzy logic in tuberculosis, fuzzy logic in cancer and lung cancer, heart-related disease, diabetic, asthma, osteomyelitis. Here comes my conclusion. Fuzzy logic theory is widely used and applied in medical field for diagnosis, prediction of disease, risk analysis, especially for the complicated cases such as heart attack, heart, cardiac disease, cancer, diabetics, drug addiction. It is based on natural language and also uses method instead of specific algorithm, with more advantages such as flexibility in structure, tolerance of imprecisions, and known for degrees of range. Here, this is my fuzzy logic systems make the computation time optimal and provides more accurate result in health science fields. These are some of my references. Thank you. Thank you, sir.
Thank you for your presentation. Any questions? There is no other question, I think. See, fuzzy is a good concept because of the inherent uncertainty present in the linguistic things, but when you the fourth or fifth slide possibly, I think in the beginning of your slides you even used fuzzy for defining the height. Yeah, I think to some extent the fine quantitative variables need not be attached with the fuzzy. So whenever there is a possibility of qualitative variables with some uncertainty, I think we can bring in the concept of fuzzy. When it is purely quantitative, it to some extent say it's artificial enforcement, something of that sort. Okay, but for that I think no artificial enforcement, so to say.
Okay.
Introducing fuzzy for the sake of introducing.
Okay.
I think, but for that, I think this is a good presentation. Thank you very much.
Thank you, sir.
I think, have you done?
Yes, sir. Yes, sir. Oh.
So in that case, I thank all the participants for their very good presentation and defending the thing with justifications. And I also thank Professor Bala and Professor Tangaraj for their very useful compliments in terms of their questions. And that will throw more light to the not only the presenter but also to the entire audience and researchers. We take more things from such discussions rather than presentation. Okay, this makes the presentation very live and active, and we are very thankful to both the professors. And I once again thank the organizers, the Department of Statistics, Madras University, the HOD, and the organizing secretary. And I will hand over the session to the organizers. Thank you very much.
So, thank you, sir. Sir, on behalf of the organizing committee, I would like to thank Professor N. Viswanathan, sir, for chair the sessions. The sessions are very nicely and very useful. I hope all the research scholars benefited from that contributory session. For information, the respected professors kindly join the another link. The link is available in the validatory function invitation. Please join that link.
Suresh, could you send me that link to me to my email address, please?
Yes, sir. Yes, sir. Yes, sir. Sure, sir. Yes, sir.
Thank you.
Thanks.